Recording.
Yeah, comes on everyone. So great. So last thing we did movement of inertia. We have written all the shapes. Yeah. Hope everyone has gone through the notes. Let's go ahead. The first thing, the no slipping condition. When do you say, two bodies are not slipping? We have done this in friction before. No slipping. Meaning two surfaces are said to be not slipping if there is no relative motion at the point of contact. Simple definition, what it simply says is if two surfaces are touching and if you say they're not slipping, right, what it means is simply at the point of contact, they have same velocity. So for example, generally, right, people have this misconception. They think, when you say no slipping, they think it is not moving. Just give a second. Others, do keep your cams on. If you say this is going with 2 meters per second, this is also going with 2 meters per second. If you see here, A and B are moving, but not slipping. Because they have same velocity. But if you look at B, and the ground are slipping because ground is at rest, whereas B is moving. So simple, don't make it complex. When someone asks you what do you mean by it's not slipping, wherever the two bodies are touching, they have same velocity or no relative velocity. It's the same thing. They have same velocity. Therefore, V relative is 0. So that's a simple definition of no slipping condition. Clear? Next thing. Velocity and acceleration profile of a rolling body. Now consider a body moving with speed V and angular velocity omega. We can study this by splitting the motion into pure translation and rotation. Let me show you how it is done. So let's say we got a wheel or something. Let this go with velocity v. And let this also rotate with omega. So it's like your cycle ka wheel which is rolling on the floor. So what I'm saying, we can split this into two parts. We have discussed this, even in centromers if you remember. So in the first case, we'll assume everyone is going with v. And the second case, we'll assume everyone is rotating with omega about the center. Meaning, if you say this point is A, B, C, D, and let's say some random point here, E. Now, if I ask you to find the speed of A or velocity of A or B or C, this is what you do. In translation, so this is A, B, E, C, and D. So this is the logic there. So in translation, everyone is going with V. Isn't that what happens in translation? Every point on the body will move in equal parallel paths. Means all will have velocity in the same direction. Means as if you're just dragging the body with V. In the second case, when you have pure rotation, everyone is rotating about the center. So in this case, it feels like it is going in a tangent, which is r omega. This is going backward with r omega. This is going with r omega. This is going with r omega. This is going with some x omega. Now, if someone asks you to find the velocity of the points, this is what you do. You get the velocity from translation, vi cap. You get the velocity from rotation, minus r omega I cap. That will be v minus r omega I cap. Are you getting how are we finding the velocity? Split the motion into translation and rotation, get the translation velocity, get the rotation velocity, add them. You want velocity at b. The translation will always give you vi cap, and the rotation would be minus r omega j cap. The velocity at c will be v and r omega are in the same direction, so v plus r omega I cap. You want velocity at d, then it is v I cap plus r omega j cap. You want velocity at e. Now for e, you have to resolve the velocity into components. So this is v and this is x omega. So these two resultant you have to take. Clear with that. We will try to find eco velocity in the next thing. So this is how you find the velocity of any point on the rotating body. Is this making sense, everyone? You split the motion into translation where every point is going in a line, and second thing, you stand on the center and think everyone is going in a circle. When you add the vector of these two, that will give you the net velocity of any point on the disk or the ring or anything. Is this clear, everyone? Yeah, let's see a question on this. That will make things more clear. We got a disk here. Radius is r. Center velocity is v. Is rotating backward omega 3v by r. We have a point A here at a distance of r by 2. This angle is 30 degrees. This distance is 2r by 3, and this is point B, and 45 degrees. Find velocity of A, velocity of B, and a point with zero velocity. So on this disk, there is a point which has zero speed. Which point is that? Where is that point located? At this instant. Remember, it is going forward with V, but it is rotating backward with omega anti-clockwise. Like I said, the idea is straightforward. Translation, everyone is going with vi cap. The rotation, everyone is going in a circle anti-clockwise. Get the velocities, get me in the form of I cap and j cap. Huh? I'm asking you velocity, not the magnitude. So you have to give me the answer in terms of I cap and j cap for A and B. Let's get them. I'll give you a minute for A, minute for B. Give it a try for a minute, then I'll show you one in case you're confused. Yeah, let me show you one for the A. This is point A. This is 30 degrees. So the translation is going V this way. The circle, it is going in a circle like this. So this will be the velocity, which is r by 2 omega, because radius is r by 2. So A ka velocities are like this. V this way, r omega by 2. And remember, omega is given as 3v by r. So r omega by 2 is 3v by 2. And how much is this angle? If that is 30, this is 30, so this will be 60. So this angle is 60. Geometry, everyone. 30, 30, that will be 60. There, you're done. VA will be V plus 3V by 2 cos 60 I cap minus 3V by 2 sin 60 J cap. That would be 7V by 4 I cap, 3 root 3V by 4 J cap. Make sense? Easy? So you just get the velocity. V tangential is r omega, that's from rotation, and V center of mass is V, that is horizontal. I cap, J cap, resolve, finish it off. Any doubts on this? Now, can you do for B, and can you find the point with zero speed? Get them, I'll give you a minute. That's it, same thing you have to do. Hmm. Let's see. Hmm. Yeah. So if you go for the B point, B is somewhere here. This will have velocity V that is going in another circle. This will be 2r omega by 3. So for point B, velocity is this way. This is 2r omega by 3, where r omega is 3v, which is 2v basically. And this angle will be 45. So velocity of B will be v minus 2v cos 45. That is v root 2 I cap. It's actually going backward, and 2v 45 to v root 2 j cap. Clear, everyone? You have to resolve the 2v I cap j cap. Now there are two components. And what about the point with the zero speed? You can kind of guess here. First thing, if you won't get zero speed, they should cancel out. So any point here, let's say from the center, if you take at a distance x, due to translation, you're going forward. Due to rotation, you're going backward with x omega. V minus x omega must be 0. And omega is 3v by r. X is equal to r by 3. So it's a point above the center. So if you want zero speed, both the translation and tangential should cancel out. It can't be below, it has to be above only. If you take the point below, V and x omega by 3 both will add up, na? It's rotating like this. They will add up. There's only one point with a zero speed. That is above in the upper quadrant. Have a look at this. Easy. So just take the point r omega that is going in a circle, V tangential, and V center of mass, and just add them. Clear, na? Devika, Devansh, Arush, Adi, Ansh, clear with this. Next one. Acceleration profile. So this is the velocity profile we saw. If you look at the acceleration profile, we can do the same thing again. But acceleration is a little more interesting than velocity. So if a body is going with acceleration A and alpha, that means you can treat every point is going with A. That's your translation. Remember, this is A center of mass actually. And every point is rotating with R alpha. See, that alpha ka direction can be anything. Huh? I'm just taking it clockwise. It could have been anti-clockwise also. So we have translation and rotation. So when you add them up, it looks like velocity, but there's one more extra thing which will come. So if you take a point here, first thing, this is the acceleration of center of mass. Okay. Next thing, because of rotation, we get A tangential, which is R alpha. But because you're going in a circle, there will be A centripetal. There are 3 accelerations at every point, which is omega square R. Isn't it? When a particle is going in a circle, you'll have centripetal acceleration, you'll have tangential, and because the center itself is going, there's an A center of mass. So don't get confused. There is a three acceleration. One is translation, and for points you have it's a circular motion. The points are going in a circle. If you take this point here, again same thing. This is your center of mass. This is your r alpha, which is your a tangential. This is your omega square r, which is centripetal acceleration. Same thing here, a center of mass, r alpha, omega square r, omega square r, a center of mass, r alpha. This is how the acceleration will be at any point. There are three accelerations at every point. Now, if I can ask a question like this, in which quadrant can you get a zero acceleration? In which quadrant can you get a zero acceleration? In which quadrant the acceleration in the j cap direction? They can ask you questions like this. Can tell me in which quadrant can you have a zero acceleration, and in which quadrant can you get an acceleration in the y-axis? Can you see and feel it here? These three can cancel out. They form their y-shape kind of thing. This is the only thing they can cancel out. You can get zero acceleration in the fourth quadrant. Can you tell me in which quadrant can you get acceleration in plus y-axis? Means when you add these three vectors, the resultant can be in the vertical direction. Can this be vertical direction? Think about it logically. See, if I resolve r alpha into components, it will be like this. Omega square into components, it will be like this. Chalo, vertical cancel hoga. Horizontal will be like this, na, forward. So second quadrant can have acceleration in the horizontal direction. It can't be in the vertical direction. Similarly, if you look at the first quadrant, same thing. First quadrant direction can be negative y-axis. Third quadrant can be in the vertical direction. Are you getting how they can frame questions? You'll get this thing as a theoretical question. They'll give 4 points A, B, C, D, and they can ask you like this. The acceleration of point A can be in which direction? Upward, downward, right, left, something of that sort. Can be, meaning there is a possibility. Is this acceleration profile clear, everyone? So there are three accelerations, A center of mass, A tangential, and A centripetal. Any doubts on this? Now, if you go for the no slipping condition for this, so for a rolling body, now this is the important one. Like I said, there are three important things. Torque, which you have already done, moment of inertia, and the third thing is a no slipping condition. So consider we have a body here on a plank. Let the plank go with the velocity Vp. Let this go with V and let this rotate with omega. Similarly, let the acceleration of the plank be AP. Let the acceleration be A and let this be alpha. Now, if someone asks you what is no slipping condition, this is the idea. See, again, what is no slipping condition? At the point of contact, they have same velocity. So at the point of contact, this point A and B are touching each other. So because of rotation, this thing will have speed V forward. This will have r omega backward because of this thing, and this point will have speed Vp. So for no slipping, Va must be equal to Vb. Therefore, V minus r omega must be equal to Vp. This is how you write. Similarly, if you try to write for acceleration, you have to satisfy both velocity and acceleration. Acceleration of this thing will be A minus r alpha. Acceleration of A will be equal to acceleration of B. This will be A minus r alpha is AP. If the plank was at rest, then Vp is 0, then AP is 0. Then you get V minus r omega is 0. Then we get V is equal to r omega. Now here, I have seen most people, they mess up this thing. Ask them what is no slipping condition, V is equal to r omega. Matlab, without thinking, blindly they say no slipping condition is V is equal to R omega. Don't do that. If someone asks you what is no slipping, simply say this thing. At the point of contact with each other, getting it? The relative motion is zero. That's it. You should not say V is R omega, nothing. Getting it? Now, that is one. Second thing, when people say V is equal to R omega, most people think this is coming from circular motion. Remember, in circular motion, you studied V is equal to R omega. That's a blunder here. Huh? Actually, what is happening here was this was V center of mass minus V tangential was equal to V Planck. V center of mass was V tangential was R omega. So V tangential is equal to R omega came from circular motion. So when you say V is R omega, this thing didn't come from circular motion. You're proving that center of mass velocity is equal to the tangential velocity. I hope you're getting it. So it is V center of mass is V tangential, which is R omega. V center of mass is not directly R omega. Similarly, A center of mass minus A tangential. Again, this is when the Planck is at rest. So I don't want you to buy hard this. Don't say V is equal to R omega. People, you ask them no slipping condition, V is equal to R omega. They don't know what they're talking about. It's a very special case when you're on a ground. And if you ask them, how did you get R omega? Circular motion ne kiya na? V is equal to R omega. Blunder. This is R alpha equal to 0. Let's see if you will get the hang of this. Is this clear, everyone? That's it. This is the meaning of no slipping condition. Whenever you have two bodies there at the point of contact, the relative velocity of the relative acceleration must be 0.
Sir.
Yeah.
So like I couldn't understand why is it a blunder that V tangential is equal to R omega?
When did I say that's a blunder? When did I
Uh,
say that is a blunder?
okay, sir. So it's just V C1 is equal to V tangential equals to V Planck.
Yeah. V tangential is R omega. Why is that a blunder? That is actually the result. V tangential is R omega.
Yes, sir.
I said don't say V center mass became equal to R omega because of circular motion.
Okay, okay. Yes, sir. Thank you, sir.
That is a blunder. Getting it? It
Yes, sir.
looks like that. It is not. V tangential R omega is right. Clear with this? Next one. Let's see a question. That would be the best thing to get things cleared. So we have a cylinder here. Radius is 2 meters. This is going with velocity 5 meter per second. This Planck, right, is going with, let's call it VP1. Let's call this thing P2. So VP1 is 2 meter per second. Find omega of the cylinder and velocity of Planck 2. There's no slipping between the cylinder and the Plancks. So there is an omega for this. I didn't give you. You have to find that. Okay, what about the velocity of the Planck? Let's see. This was straightforward. Take the cylinder ka velocity to be some omega. This is going with v. So at the bottommost point, the velocity is v r omega. At the topmost point, the velocity is v and r omega. And now you are going and touching this point here, and you're going and touching this point here. So this point ka velocity is vp1, and this point ka velocity is vp2. Since it is not slipping, vp1 must be equal to v minus r omega. V plus r omega must be equal to vp2. Isn't that the meaning of no slipping? Wherever you're touching, those 2 points should have same velocity. Now vp1 is given as 2, v is given as 5, r is given as 2, and this is omega. So omega is 3/2 radians per second. This is v, and r is 2, and omega is 3/2, and this is vp2. vp2 is 8. Easy? This is what I'm saying. If you blindly say v is r omega, you're gone. So that v is equal to r omega would come if this thing had been on the ground and the ground was at rest. Is this clear, everyone? Got this? Let's see one more like this. This is the ground here. No slipping. Radius is 2 meters. This is point A and this is 60 degrees. This is going with 10 meters per second. Find VA. You need to ask yourself. They didn't give you omega if you observe. Now, suppose if omega was not there and if this was ground, it will just slide on the floor. How can it not slip? It would slip, right? That means there is an omega which is not telling you. So you need to understand that. Every time they won't see the body is rolling and everything, they'll simply go like this. So it is understood there is an omega in the question, or else this point would skid on the floor. So indirectly asking you to find the omega and then find VA. Get this. This would be a proper mains level question. Uh, 59 5 root 3 12.25 2.5. Okay. Again, same thing. So first thing, at the bottommost point, you have V here and R omega here. So V minus R omega must be equal to V ground. That is a no slipping condition. Always, keep that in mind. Always, if it's okay if you write V is equal to R omega, but at least in your mind, tell this thing. V minus R omega become equal to V ground, and V ground is 0. Therefore, this was 10 to omega was 0. So omega was 5. Don't directly say, understand that point. That's it. That is the only thing. I have seen most people messing it up in a flow in the exam, right? That's what happens. So this guy is going with V and this guy is going with R omega. Just be careful with the angles. If this was 60, this was 90, this was 30, this was 60. And V is how much? V is 10. R omega is also 10. You're done. So velocity of A will be 10 plus 10 cos 60. That is 15 I cap. 10 sine 60 minus 5 root 3 j cap. Easy. This is a proper mains level question. Any doubts on this? Great. Let's see a little higher. Let's say we have two cylinders and we have a plank on top of it. We have one more plank and we have two more cylinders. And this is the ground. Let's call this thing P1. Let's call this thing P2. So this bottom cylinders are rotating with omega. These cylinders are rotating this way with 3 omega. All cylinders have same radius. There is no slipping anywhere. There's no slipping on the ground. There's no slipping on the cylinder and the planks. There's no slipping at any surface. Now see, if you're just rotating here, it would skid, isn't it? That means there is a transition velocity, which I'm not telling you. Find the velocity of the cylinders and the planks. Idea is still the same. The point where you are touching, they should have same velocity. Get them. Lower cylinders have R omega, P1. Get everything? Yeah, that may be right. Meaning lower cylinders both will be same only, na? So there's no need to find. Upper cylinders is 3R omega. Okay, that maybe. I'll give you another 30-40 seconds. I'll show you then. We have so many different answers. R omega, 5R omega. Someone got omega into 3 plus R. God, your dimensions are not matching. Understand one thing. It's okay if you don't know the right answer, but when you see a blunder, it should know it's a blunder. Hmm. Okay, let's see. Let's start with the lower cylinders. I don't know how they're going, so I will assume it is forward. Don't worry about that. Science will take care of it. This is omega. So this point is V1 plus R omega. This point is V1 minus R omega. On top of this, you have this Planck here, which is going with Vp1. And this bottom is V ground. I'll write Vg is 0. So V1 minus R ground is Vg. V1 minus R omega is 0. So there, V1 is R omega. This was straightforward. The upper one, V1 plus R omega, must be equal to Vp1. V1 is R omega, so we get Vp1 is 2R omega. Perfect. Then when you take the upper cylinder, again, I'll assume it is going forward with V2, but be careful. This time omega is backward. That means this point will have a velocity V2 plus 3R omega. I hope you have taken that into account and not blindly have taken omega forward. And this point will have V2 minus 3R omega backward. You have to be careful omega is in which direction. If you see, this is anti-clockwise. Lower cylinders are rotating clockwise. This would be your Vp2. Now, these 2 points are not slipping. So V2 plus 3R omega is Vp1. But Vp1 is 2R omega. So V2 is R omega. It's going forward. Vp2 is V2 minus 3R omega, but V2 is R omega minus 2R omega. That means the Planck is actually going backward. So this upper Planck is not going front, it is going back. So you don't worry about the directions. You take forward, negative, doesn't matter. The science will take care of it. I'm pretty sure most of you goofed up this part here. You didn't take anti-clockwise direction. You have taken 3R omega forward. Please check your answers. Ask me if you're confused. So the Planck 2 is actually going backward. It is not going forward. V2, okay, V2 is minus R omega. I wrote that wrong. Then this also will be minus 4R omega. Both are going backward. My mistake. Check it out. Any doubts on this? Anyone not clear with this? Clear? Next one. Next one. Let's see one more like this. We have a cylinder. Planck is going with V. So basically, this is a string which is wrapped around the cylinder. And that string is taken back and connected to the plank below it like this. Find the velocity and omega of the cylinder. There is no slipping between the cylinder and the plank. Two V and V by R. Okay. Anyone else? I'll give you a minute more. Vihan got 0 and V by R. Okay. You have different answers. Okay, let's see. So take the cylinder, take the plank. Let this go with V1 and let this go with V dash. And let this rotate with omega. So at this point, the speed will be V dash minus R omega. At this point, the speed is V. That's your no slipping condition. So V dash minus R omega is V. That is the meaning of no slipping condition. Next thing, if you look at here, the string is attached here and it is attached to this point here. Now, velocity along the string must be same. This is the string constraint from laws of motion, everyone. If the velocity along the string is not same, then the string will either stretch or the string will break. So if you look at this point here, it is going forward with V dash plus R omega, and this guy is going with V. So be careful here. Velocity along the string, that means this point is going backward with minus V dash minus R omega, and this should be V. So minus V dash minus R omega is V. That is the meaning of it. Velocity along the string. If this is pushing 1 meter per second, this also should go 1 meter per second along the string, isn't it? The signs have to be taken care. This was your equation 2 and this was your equation 1. Add 1 both of them. If you add 1 plus 2, V dash will cancel. You will end up with omega is equal to minus 2 r omega is equal to 2V. We get V is equal to minus r omega, or omega is equal to minus V by r. So I have taken the direction wrong. Wait. And then they do cancel out. And if I substitute this thing there, yeah, and I'll get V dash is equal to 0. Meaning, interestingly, the cylinder is just rotating anti-clockwise. It's not rotating clockwise like I thought. And the upper cylinder is not moving only. Cylinder is at the same place rotating. So your final answer is like this. So this thing has zero speed and this guy is just rotating with omega. Is that making sense, everyone? So cylinder has no translation. Cylinder has only rotation. So that keep these things in mind, don't always think like it has to go with some rotation and translation when I say no slipping. Yeah. Great. There, that is how, this, how did you get the top speed? It's V plus R omega, isn't it? V dash is going forward, R omega is also going forward.
Sir, for the
Sure.
string you have written minus V.
Minus, na? Because that point is actually going forward, right?
Oh, okay, sir. I got it.
The point is actually, if you see here in the diagram, it is going forward. But if the statement says velocity along the string must be same. So how to make this backward? By putting a minus sign.
But sir, if it is forward in the first place, then the velocity of the string wouldn't be same, right?
You're getting confused unnecessarily. If I say I'm going minus 5 meters forward, means what?
5 meters backward.
Or if I say I'm going 5 meters backward, both are same only, na? Just a minus sign. Can I say like this? I'm going forward, V dash plus R omega, or I'm going backward,
Oh, I
right?
got it.
Minus V. Minus of a minus था. अगर चलो वो confusion हो रहा है ना, काम करो. Then just treat this thing as V dash and make omega this way. That also would have worked.
Yes, sir.
Yeah. Why do make it so complex, right? Just because you're getting the answer. Why didn't you try to do that in this problem then? You should try to do that. Why बोल रहा हूँ? Just because you're getting the answer, don't try to generalize everything. Next thing. When you feel like that, ask yourself, 2 into 2, right, is 2 plus 2. Then can I say 3 into 3 is 3 plus 3? Because it is working here, what is the problem? That is the thing. So there, now you know no slipping condition, you know all the basics now. So let's see. So how do you solve equations? Steps to solve. Step 1, choose a system, draw your free body diagram. Standard one. Step 2, assign linear and angular accelerations. Meaning if there are bodies, then use A1, A2, A3. If there are bodies rotating, use alpha 1, alpha 2, alpha 3, and so on. Right? And find relation between them. Using constraints, which you have learned in NLM. string constraints or rigid body constraints, and no slipping condition. Now we have one more technique. Then you can use your NLM or no slipping conditions. You have to find the relation between A's and alphas. Third, apply F is equal to ma along x and y axis. So resolve your forces, resolve your accelerations along x and y axis, and apply xf is equal to ma. X and y, you can choose any two perpendicular axes. Fourth, apply torque is equal to I alpha. Preferably, choose the hinges, right? Basically, you can say fixed points, fixed axis. Generally, hinges, which are supporting to the ground. Sometimes hinges also can move, but preferably take something which is not moving, fixed axis, or center of mass, or basically any axis in the inertial frame. Preferably, because if you take something which is accelerating, you have to introduce pseudo force. So that is the only thing. There's nothing like you can't take about any axis. So then your equation becomes like this actually. If you take about any axis, then it will be torque due to external plus torque due to pseudo force will be equal to I alpha. So it can be taken. But out of all, center of mass is a special point. Now, let's say your center of mass is accelerating with A. If you go and stand on center of mass, aren't you standing on a non-inertial frame? If your system is accelerating, if you go and sit on the center of mass is accelerating, agreed? So you're standing in non-inertial frame. Where do you apply pseudo force? When you apply pseudo force on the body, where do you apply pseudo force? You apply pseudo force on center of mass, isn't it? Now, if you take torque about center of mass, pseudo force ka torque kya hoga? Zero. You get the thing? Center of mass is very special in that way. Even if the center of mass accelerates, you're getting it. The pseudo force will go and act on the center of mass. So torque due to the pseudo force will be always zero about center of mass. So that is the reason center of mass works even in non-inertial frames. So about center of mass, the torque due to pseudo force is zero since pseudo force passes through center of mass. Just like mg is passing through center of mass, mg is drawn from center of mass, pseudo forces are drawn from center of mass. So your center of mass will always work. So sometimes if you get confused about which point, what and all, don't find a fixed point, take center of mass. That's the safest one. Solve the equations. Clear? Let's see the equation. Have a look at the steps once. Let's see. We have a rod here. This is hinged. This is a string here. Lambda is equal to lambda naught x, non-uniform rod. This is x is equal to L and this is x is equal to 0. And this string is cut at point A. Find alpha of the rod, acceleration of point A, and hinge reactions just after cutting. Find acceleration of center of mass also. There, let's get this. I think I gave a tough one. I'll help you see. First thing, when you draw the free body diagram, you have to write mg. Where will you write mg from? Center of mass, isn't it? So first find the center of mass. Find the mass of the rod. Find the moment of inertia of the rod. So you literally have to integrate. And that we have done all these things in the class. I taught you how to find the center of mass for this rod. I taught you how to find the moment of inertia for this rod. You know all this stuff. Start with that. Find the mass of the rod. Find the center of mass of the rod. Find the moment of inertia of the rod. I could have taken a uniform rod, but yeah. Let's get the basics ready. So x is 0, x is L. The distance we take a small dx. So dm will be lambda naught x into dx. So mass of the rod will be integral dm 0 to L, which is lambda naught L square by 2. Then x center of mass is integral x dm by integral dm. I remember the answer 12 by 3. And the moment of inertia I about the hinge is integral dm x square, which is lambda naught x cube dx. That is lambda naught L power 4 by 4. That's your moment of inertia. You should know the mass, you should know the center of mass, you should know the moment of inertia. Everything you'll know. Now the question starts. Step 1, choose a system, draw the FBD. Hinge reaction, Ny, Nx. Now where will you keep the Mg? Mg is placed at the center of mass. This was Mg. What distance? 12 by 3. That's it. There is no other forces. Step 2, assign accelerations. This is alpha. Now remember, center of mass is going in a circle. This is a center of mass which is going with R alpha, which is 2L by 3 alpha. Center of mass is going in a circle. That's the relation between them. Step 3, apply force equations and torque equations. First, I'll apply the torque equation. I will take the torque about the hinge. Why? Hinge is at rest. So torque about the hinge will be equal to I hinge alpha. Remember this. If you take torque about A, I also should be about A. If you take torque about something, I should be about that same thing. So torque about hinge will be mg into 2L by 3. I taught you how to get the torque. I hinge will be lambda naught L power 4 by 4 into alpha. What is M? M is lambda naught L square by 2. Perfect. So lambda naught goes off, 2 goes off. This is L cube, so 2 goes off. So this is G by 3, 4G by 3 L. That's your alpha. I hope I'm right. And then A center of mass will be 2L by 3 alpha. That is 2L by 3, so 8G by 9. Yeah. Then apply force equations. In the horizontal direction, Nx is 0. There is no horizontal acceleration. Vertical direction, Mg minus Ny is equal to M into A center of mass. From here we'll get Ny is equal to mg minus macy. You know all the values, substitute there. This would be mg minus this thing, mg by 9. What else did I ask you? Acceleration of this point A. That is easy. Acceleration of A will be L alpha 4g by 3. Check your steps. Any steps are not clear. So that mg has to be drawn on center of mass. So if you need to find the center of mass composition, how much is the mass? That also you need to find, because mass is not constant. Moment of inertia is not ml square by 3 because it's not a uniform rod. So that also you have to find. That's it. That is the main thing. It's not a tough problem, but yeah, it has multiple steps. Any doubts on this? Clear with this? Clear na, Poroja? Vihan, Niharika, Ariman, Devika, Ansh? Clear? Adi, Arkush, Sharman? Sharman, not there. Okay. Let's see next one. Let's see a little easy one. Uniform rod, mass m length L. Theta, there is no slipping. The ground is rough. This is cut. Find alpha, normal reaction and friction just after cutting. The floor mate is not slipping, meaning after some time it will be like this. After some time it will be like this, meaning this point, right, behaves kind of like a hinge only. If that point slips, the diagram would have looked like this. The point will be going backward and the rod is falling like this. This is a little easier than the previous one. Step 1, choose your system, draw the FBD. Step 2, forces, alphas and accelerations, find relation between them. Step 3, force equation. Step 4, torque equation, solve. The steps are the same. No matter what kind of thing I give you, that is the order you follow. There is a theta also, God. Without theta, already get the answer. Right, Vihan. We forgot a G. Let's see. Normal reaction, friction, mg will act on the center of mass. SN accelerations, this guy is going with alpha, this point is fixed, to central mass will be going in a circle. This angle is theta. So this angle will be theta. So this will be the horizontal acceleration AX, which is A center of mass sine theta. This will be the vertical acceleration AY, which is A center of mass cos theta. And how much is A center of mass? A center of mass is L by 2 alpha, because it's going in a circle of radius L by 2. This distance is L by 2. Next thing, I will take the torque about the bottommost point. Why? It is not slipping, so it's an inertial point. Torque about A, only mg ka torque will come mg L by 2 cos theta, the perpendicular distance. That is equal to I about A into alpha. If you take torque about A, I also must be about A. It's a uniform rod, so ml square by 3. Alpha is 3g by 12 cos theta. This was the mains, I think, 2018 question, I guess. Straightforward, find alpha. Next thing, you want to find the friction in the normal reaction. Friction F is equal to mass into AX. That is the only thing there. And AX will be A center of mass, which is L alpha by 2 sine theta. Alpha ka value I know, you can substitute there, and that would be 3 mg by 4 sine theta cos theta. That's your friction at this instant. Similarly, vertical direction mg minus n is equal to m into ay, which is mg minus may. This is m. L alpha is 3 mg, so 3g by 4 sine square theta, cos square theta. So mg 1 minus 3 by 4 cos square theta. That mean you're done. Like I said, once you got the A center of mass split into X, AY, just use F is equal to MA. So when you're writing F is equal to MA, you choose your forces and accelerations in along X and Y, and then you solve. Since center of mass is going this way, I have to resolve that into AX and AY. Is this clear, everyone? Check out the steps. Just follow the process. Nothing new. The only new thing, technically, if you see, the only new thing is you did torque and the no slipping condition. Everything else kind of looks like NLM ka steps only. We just added 2 more things. Clear, everyone? Take a break. Come back with 7.5. We'll continue from here. Any doubts so far? Okay, come in 10 minutes.
இருக்குல்ல ஒண்ணு.
Let's see the next one. Similar one. Let's see if you have a square plate. Square plate, mass M, side L. The string is cut here. Find alpha, acceleration of center of mass, and the hinge reactions just after cutting. Gravity is there. Similar to the previous one, only in place of a rod, now we have this thing, a square plate, and the left side is hinged. So basically that point is fixed. Again, remember the process steps are still the same. FBD equation solve. Everyone should try. Okay. G by L. You didn't get any alpha or something? Yeah, that is wrong. You're wrong, Vihan. Hope everyone got the FBD. There are only three forces, Ny, Nx, and Mg. The center of mass is going in a circle of radius L by root 2. Hope you have taken that properly. It is half diagonal. A is not equal to L alpha. That looks right, Adi. Let's get the remaining also. Let's see. Step 1, free body diagram. Ny, Nx, Mg. Step 2, Sn acceleration, alpha. This is your center of mass. That itself is going in a circle. This is a center of mass, which is L by root 2 alpha, because this would be the radius. And that angle is 45. So this is AX, which is a center of mass cos 45, because this is 45 and this is 45. AY is also a center of mass cos 45. Luckily, both are equal because it's a square. There, I know everything. This is the hinge. Torque about the hinge is I about the hinge into alpha. Torque about the hinge, mg. Perpendicular distance is L by 2. I about the hinge is how much? It's not ml square by 6. You have to use parallaxes theorem. Ml square by 6 plus m L by root 2 whole square. This is I center of mass and this is md square. That's what I said. If you take torque about the hinge, then take I also about the hinge. This would be mg L by 2 and this would be 2 by 3 ml square alpha. So we get alpha is equal to 3g by 4l. A center of mass is L by root 2 alpha, which is 3g by 4 root 2, 3g by 4 root 2. Adi, I think where did you mess up? You got an extra 2. Check it out. Once you got this, next thing, force equation, horizontal direction, nx is equal to max, which is MSEM cos 45. Mg minus ny is equal to may. This would be mg minus macom sine 45. I will leave the equations to you. You can solve. That you will get the ny from here, you'll get nx from here. Check. If you solve this, this would be 3g by 4 root 2. This will be 3mg by 8. This is 5mg by 8. I think I'm right. Check. That's your answer. See where you goofed up. Maybe you messed up the ICA value, or maybe you messed up the ARCA value, radius of the circle. Somewhere you have to be careful about each and everything. Anything that you're not clear here, please ask. All got this. Next one. Now, if you observe one thing here, all these questions we are doing so far, there is a fixed axis. There is a fixed axis rotation. These kind of problems are called fixed axis rotation. So the axis is not moving. Later on, we will see when the axis also moves. We have a disk here. This is a rough ground. Mass m and radius r. So someone spinned this with omega naught and they placed it on the ground. Able to visualize how it is? It's like this. We have a disk here. So someone spinned it like this and they kept it on the ground. So when you do that, what will happen? It will spin, 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 and eventually stop, right? You're able to visualize? It's like a dosa. You rotate this and keep it on the flow. So it rotates, 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 and finally slows down and stops. So find the time when the disk stops rotating. A rotating disk is placed on a rough floor as shown. Find the time when it stops rotating. Let's get this. It's a good one. We will see something like this again in viscosity and electromagnetic induction. But the idea is the same. Anyone didn't get the diagram, please ask me. How is the friction here? See, if you try to look at the picture here, if you say this guy is rotating with omega, I told you multiple times, you see a disk, the first thing when you choose elements, we have to take thin rings. So you take a thin ring of distance dx. And if you look at the friction here, this is how it looks. Friction will be backward. So friction will be circular. So if the disk is rotating anti-clockwise, friction will rotate clockwise. Both will be in the opposite direction because it is skidding. Now, if someone asks you what is the friction on the disk, what will be the friction on the disk? How much friction force is acting on the disk? If this was a question, net frictional force on the disk is 0. Why? Friction is a vector quantity. So this friction will cancel. This and this will cancel, and so on. For every one friction, there is one more friction in the opposite direction. They all will cancel out. Okay, the vector's friction cancels out. But if they ask you torque doesn't cancel out. Torque due to friction is not 0 because they cancel out here. Because if you remember, torque is a pseudo vector. It goes out of the plane. So the torques will all add up. So the disk will not have any, acceleration of center of mass. So this thing is fixed at the center and it is rotating. It behaves like that. So if I take this small ring, this is how it looks. The friction is acting this way. we have normal reaction, we have dmg. What is dm? Dm is total mass of the disk by total area into the area of this thin disk 2 pi x dx. What is a normal reaction? Mg. So what is friction? Mu n. This is the friction on the ring, which is mu dmg. This would be 2 mu mg x dx by r square. This is the friction on one ring. Then what is the torque on the ring? Torque on the ring is the radius into the friction on the ring, the perpendicular distance. So this would be 2 mu mg x square dx by r square. And remember, all the rings are connected to each other. So you just can't take one ring. So you have to find the total torque on the disk. That you get by integrating all the rings. The limits will go from 0 to r. 2 mu mg by r square integral x square dx from 0 to r. So we get the torque on the disk will be 2 mu mg r cube by 3. That will be 3 into r. But I know torque is nothing but I into alpha. And we know I of the disk is mr square by 2. From here we get alpha is equal to 4 mu g by 3r. And which you notice it is constant actually. Therefore, I can use omega final is equal to omega initial plus alpha t. Finally, the disk will stop. This is omega naught and this is minus alpha t. From here we get the time, which is omega naught by alpha, which is 4 mu g, 3r omega naught by 4 mu g. Once you got alpha, it is just a matter of circular kinematics. Have a look at the steps. You cannot do it directly. You have to take a ring, because see what is happening. For every ring, did you observe one thing? Every ring has a different mass. Every ring has a different friction. Every ring has a different radius. So you have to find the torque on each ring and then add all the torques, then you'll get the total torque on that disk. So when you apply the formula, torque is equal to I alpha. The tau is the total torque on the disk, is I of the disk into alpha. Please have a look at this. This problem's right. You should definitely try this on your own after the class gets over. You should take a rough paper and try them on your own. If you don't do these things, you will forget. And when next time when you see this, this will be, vaporized out of mind. So have a look at this. Ask me any step you're not convinced here. Exact same problem, similar one, again we'll encounter later on in other chapters. Idea is the same. Like I keep telling you every time, when I have to take an element for a disk, we always take disks. Idea is the same. Any doubts on this? Anyone not convinced with any particular step here? Yeah, great. Next one. They can even ask this question. The disk is placed on the ground. How much torque should you apply to make it move? You should apply this much torque. If you want the disk to start rotating, you need to apply 2 mu mg r by 3. It's a good one. Clear? Next one. Let's say we have a pulley here with a block. Block ka mass is m. This is a disk, mass m, radius r. There is no slipping. So basically here we got a string here, string wrapped around the cylinder and tied to this. So basically, pulley can be treated like a disk. Gravity is there. Find the acceleration of the block. If the whole setup so matlab this whole setup, right? Let's say is inside a lift or something. Is accelerated up with a naught. Then find acceleration of the block. First, let's find normally when the system is at rest. Actually, you can do the second part directly and put a naught is equal to 0. That will give you the first part. Steps are the same. FBD, no, there are two FBDs, the pulley and the block. Assign A and alpha, find relation between them, force equation, torque equation, solve. The step or the process doesn't change. Idea is still the same. Yeah, 2G by 3 for the first one. Let's see. I'll do the second case. So step one, draw the free body diagrams. Actually, second case, right, you can also use G effective and solve, but let's see. There's a tension T dash, your own weight mg. There is a tension T here, there is a tension T here, and your own weight mg. The T dash and mg you won't require, but you should know there is a tension. Next thing, let this be alpha, let this go with A. Now, what is the relation between them? Don't blindly say A is equal to R alpha. Are you getting it? This whole setup, right? Don't forget is also going up with A naught. So now when I draw the no slipping condition, this guy is going up with A naught and this guy is also rotating with alpha. So this point is going with A naught upward and going down with R alpha. This is connected to a block. And this block here is going with A block. So the no slipping condition says if I take this point A and this point B, acceleration of A must be equal to acceleration of B. This is a no slipping condition, not A is equal to R alpha. How much is that? So that would be R alpha minus A naught is equal to A. This is your equation 1. Keep that in mind. All these accelerations are in the ground frame. Then we'll write torque about the center. T dash ka torque is 0, mg ka torque is 0. This will be T into R is equal to I alpha. I about the center is mr square by 2 because it's a disk. T is equal to mr alpha by 2. This is your equation 2. This would be mg minus T is equal to ma. This is your equation 3. There, you know everything. What do you want to find? You want to find acceleration of the block. Means I don't want tension and alpha. So substitute here. This would be mg minus m capital R alpha by 2 is ma. And from here R alpha is a plus a naught. Substitute that also. Mg minus ma plus a naught by 2 is ma. So this would be mg minus m by 2 a naught by m plus m by 2. Yeah, that's your answer. Check it out. And 2g by 3 you will get if you took both the masses are equal. I give small m and capital M. So you want to find the first case, put a naught is equal to 0. That will be the first one. Is this clear, everyone? You could have done this way also. Let this whole system be inside a lift. Then gravity will become g effective, which is g plus a naught. So basically putting the observer inside and solving the problem. Then whatever answer you get will be in the lift curve frame. So you have to bring it back to the ground curve frame. But this is how you normally solve. Have a look at the steps. I drew the FBDs. This is the no slipping condition. I wrote the equations and I solved. Keep the process simple. Don't make yourself confused and try to do complex, weird things. Yeah. Next one. I'll teach you a faster way to do this. There is a way to get these answers, but let's try to do it normally because the shortcut will not work every time. You should always know how to do it normally. Shortcuts will come later. Suppose if I give you like this. So we got a big pulley here. So we have a string wrapped around it. Here we have the block M. Okay. Let this disk be 4M, 2R. It's a solid cylinder. I'll do one thing. Let's take it as M only. This is also M and R only, solid cylinder. There's no slipping anywhere. Find the acceleration of the block. Now, before going ahead, let me tell you a few things here. So whenever they say there is no slipping, Now, see, this is what was happening. Till now, in all the problems we did, right, this was the scenario. The pulleys we used in NLM were smooth. So if this was the pulley, na, this was happening. The rope which was there, the rope was actually sliding over it. You're getting it? So till now in NLM, the pulleys never rotated. Now, if it is not slipping, what is the meaning of this? If this was the pulley and this was the rope, they're going together. Are you getting how it is? They're going together, meaning the rope is sticking to the pulley and then rotating it. If the pulley was smooth, the string will simply slide over it. I hope you're getting the difference. So basically, when pulleys, if the pulley wants to rotate, if there's no slipping, there must be a friction. So this was what was happening. So in loss of motion, when you took smooth pulleys, and when you took a rope, so if I consider this point as A and this point as B, pulley never rotated. So after some time, what would have happened? So when the rope has come like this point A must have come somewhere here, but B is still here only. Are you getting it? The pulley, the rope is simply sliding over it. So there is slipping. And if you look at the tension on both the sides, tension is same on both the sides. Because there's nothing to stop you. It is smooth. But if you take a rough pulley, so all these pulleys, when you say there's no slipping, they have friction. If this was A and this was B, this pulley has actually rotated. If this is A, this is B. So if you see, both have rotated. Pulley rotates. There is no slipping. And because of this, now if you look at the FBD of the rope, so there is a friction on the rope. Similarly, if you look at the pulley also, there is a friction on the pulley. That's why it is rotating, because it is rough. So the main theme here is the tension will be different. All the story what I told you is primarily for this purpose. So whenever I give you a question like this, and if I say the pulleys are not slipping, you cannot take tension is same. Meaning, agar yahan pe if you take T1, this has to be T2. The tension is not same. The tensions will be same if the pulley is smooth. If the pulleys are rough, or if the pulleys are not slipping, when they use the word not slipping, meaning there is a friction on the pulley, that's why it is not slipping. Is this page clear, everyone? So the difference between pulleys in loss of motion and the pulleys in rotation are, right? In rotation, the pulleys don't slip. And how do you know it is not slipping? You will see the question. Did I ever give you the mass of the pulley and radius of the pulley? That would be a general hint. And second thing, they'll use the word no slipping. Is this thing clear, everyone? Got the idea here? Now can you try? So that is one new thing. So if you have a pulley which is not slipping, you can't take tension same on both the sides. Then the story is the same. Choose your system, draw the FBD, write equation, solve. Let's see your free body diagrams. So we have this pulley, we got this big pulley, and we got this block. So let this be tension T1, let this be mg. This tension is T1, this tension is T2, this tension is T2. I'm not taking the main strings, so we don't need them. Next thing, assign accelerations. Let this be A, let this be alpha 1, let this be alpha 2. Be careful, both of them won't have same alpha because the radius is different. Now find the relation between them. So to find the relation between them, if you look at this point here, this is going with 2r alpha 2. This point is going with r alpha 1, and both are connected by a string. This point is going r alpha 1, and this point is going with the block with a. You can clearly see the constraint. So a is r alpha 1, 2r alpha 2. So basically alpha 1 is 2 times alpha 2. So for convenience, let's do this. Let alpha 2 be alpha, alpha 1 will be 2 alpha. Okay? So both will have different angular acceleration. They won't have same alpha. And a is equal to 2r alpha. Fair enough. Any doubts on this part, please ask me. So there are two constraints here. There's a relation between the pulleys and there's a relation between the pulley and the block. Any doubts on this page? Please ask. Constraint should be clear. Then you're done. Actually, question over here. Now, force equation mg minus t1 is equal to mass into acceleration. And for that guy, if you take the torque about the center, t1r minus t2r is equal to I of the pulley, which is mr square by 2 alpha 1, which is 2 alpha, mr square by 2 into 2 alpha. Simplify this. This will be t1 minus t2. R will cancel, 1, 2 will cancel. We get mr alpha. This is equation 2. And for the second one, there's only one force. T2 into radius is 2r. Don't forget this. Moment of inertia, mass is same. I gave the same mass, but radius is double. So disk it is mr square by 2 alpha 2. So this guy would be T2 m 2r by 2 mr alpha. Interestingly, we got both T1, T2, not same, but it is different there. Where we got the equations. Check your equations. Locker equation, torque equation on the first pulley, torque equation on the second pulley. This is the equation for small pulley. This is the torque equation for the big one. Once you got, it's just a matter of solving now. I'll turn the page. mg minus t is ma. T1. T1 minus T2 is mr alpha. T2 is mr alpha. A is equal to 2r alpha. There. These are all the equations that we have. Substitute here. Dump T2 here. Then we will get T1 will be 2 mr alpha. Dump this thing here. So T1 will be ma. Dump this thing here. We will get mg minus ma is ma. A is equal to g by 2. Clear? Have a look at this. Once you got the equation, it's just a matter of solving. So the main idea in these kind of questions, when you have multiple pulleys, make sure the tension on both the sides of the pulleys can't be same. Why it can't be same? Because there is a friction on the string. Because if there is no friction, the pulley won't rotate, and if the pulley doesn't rotate, it will slip. But you have given in the question, it is not slipping. That means there has to be a friction on the pulley. That is something you have to figure it out. They won't tell you all the story, what I wrote it in this page, that you need to figure it out. Have a look at these things. Is this clear, everyone? Any doubts on this? So if you see all the problems you have done today, these are fixed axis rotation, meaning there is a fixed axis and you could solve. What happens if the axis moves? Now, these things we'll be handling in the next class, but I wanted to give it a try. I'll give you 2 homework problems, try them and come. And interestingly, these things we have done today, but I'm going to change something. Same question, we have a rod mass ml theta, but this time the ground is smooth. And you're cutting the string here. What will happen? Now the rod will slip. It will become like this now. The rod will actually start going backward. Same thing, square plate. So the same questions we have done with the hinges and all, but this time we are cutting it. These are strings. Find alpha just after cutting. These are pretty good ones, right? They look more simple, but they're actually pretty good ones. You should definitely spend some time, try these 2 questions. So Thursday when we meet first thing in the class, we'll be discussing these 2 and then we will go ahead. So the next class we will start off with when there is an axis, a rolling motion, spheres will start rolling and all that stuff. We will do a few more problems on this pulley based also. I think next class it will be all based on rotations and stuff. So the major part is there, all these moving things. I think in the next week we will do energy and everything and angular momentum. I think we should be able to wrap up the chapter another 4 to 5 classes max. Okay, so with that we'll wrap up for the day. Yeah. So we have done almost 41 questions are there. So do try to resolve the paper. That is the most important thing.